Okay, we're going to look at how to set up an integral to find a volume. And I wanted to start with something that we knew. Okay, and so I'm going to start out with this box thing right here. Now, obviously some of our box just fell down. Our what are these things called? Cubes, our blocks, yes. So how would we find out? I mean, because we can think about volume like the number of cubes in this box. The idea is the same. The concept is there. So how do we do that? Well, we know that the volume equals length times width times height. And in here, my length, we're going to say is, this way. Our length right here is going to be, how many blocks is that? 1, 2, 3, 4, 5. Our length is going to be 5. Our width is going to go this way, and that's 4. So I'm going to multiply it times 4. And then we have the height. So how high is this thing going to be? It looks like our height is going to be 4. So we have length times width times height, and so I multiply by that. And so when you multiply all those together, 5 times 4 is 20 times 4 is going to give you 80. Our volume of this shape right here, this box, is going to be 80 cubes. We don't have to say inches cubed or anything like that, because we're going to say that our units for this example are cubes. All right, so in order to make a connection to what we're working on in our subject, we're going to stop thinking about L and W as separate things. We're just going to say that makes the area of the base. And then we multiply it times the height. Now, if we think of it like that, think about the base right here. How many cubes are in the bottom base? That would be 5 times 4. That would be 20. So really, what I want to change our thinking into is base times height, so it would be 20 times 4. And why are we multiplying it by 4? What does 4 represent? Not just, don't say height, but what does 4 represent in terms of the base? Yeah, how many layers, like how many bases we have. And so I guess we could think about it like this. And so far, you guys should all be thinking, well, you're just saying the same thing over and over and over. But I'm trying to make a point. Just stay with me. Okay? So we have 4 layers, so we have 4 20s, and we add them together. Oh, stop it. Of course. I said, as soon as it comes out, I just go, you would think that we'd all grow up, but I guess we never do, right? All right, so now, how can we write this? Now, instead of saying BH, how can we write this as an integral? This is what your integral would look like. You would write 20, and then you would say from 0 to 4 of dx. Okay? Now, I'm just throwing it up there. I haven't conceptually got you guys to the point of understanding why I wrote it the way I did. But I kind of want to show you guys what happens when we use the fundamental theorem of calculus on it. If I do the antiderivative of 20, that's going to be 20x. You guys agree? Okay. And then I'm going to plug in the 4, and I'm going to plug in the 0. When I plug in the 4, I'm going to get 20 times 4. And when I plug in the 0, I'm going to get 20 times 0. And then I'm going to get 80 minus 0, which just gives us 80. So again, we got 80 for our answer. So how did that happen? Where did the height come from? All I have right here is the base, 20. Where did the height come from? It came from the upper bound, right? The lower and upper bound. It goes from 0 to 4 layers. And so when we do that, we get 80. So how does this connect to a more complicated problem? A problem like finding the area, finding the volume of this pyramid. Okay, how does that connect to it? Now this pyramid right here isn't exactly like this pyramid, but I wanted to show you guys how it would look if we were to do something with Riemann sums in order to figure this out. Because I can relate Riemann sums in order to find the volume of a shape. But I'm going to talk about that in a little bit. I want to stay on topic, stay on course from what we were just talking about. So, look at these pyramids right here. What is different about these pyramids? What is changing in each of these pictures right here? Y is changing. What else? The area of the base. Now you're calling this square right here that's moving up, you're calling that the base, right? Is that what you said? Okay, that's cool. Now, it's not good to use the word base because whenever we say base, we're thinking about this bottom square down here. So I'm going to give you guys a new word to use. Instead of calling that base, call it a cross section. The cross section is always going to be the same shape as the base. And so that's why it makes total sense to call it a base. But we're not going to call it base, we're going to call it a cross section. The cross section is what's moving up. A cross section, if you were to have like a sword right here and you chop this pyramid right, straight, then you're going to see the shape of the base. Okay, so the area of the cross section is changing and the y is changing. Cool. Now, earlier we were talking about. So earlier we were looking at this guy right here. We found the area of the bottom layer, and then we just add them all together to find the volume. Okay, I want you to picture this, to find this volume right here, I want you to picture our layers being like thin sheets of paper, where you actually find the area of the paper, and then you multiply it by the height of the paper. And that's really, really thin, right? The height of the paper is really tiny. We have to have a special instrument in order to measure that. What we're going to do is we're going to find the area, the volume, of each paper, and then add them together. That would be an incredibly large amount of areas, wouldn't you say? Yes, it would. It'd be crazy. Especially when you consider that this area, this cross-section, keeps changing as we go up. The paper doesn't stay the same size. It's not as simple as this one right here where the layer stays the same size every single time. And so we had the same layer every time. We just had to multiply it by 4. Okay, but here the layers are changing as you go up. So what is changing? The area. Now, why is the area changing? What's affecting the area?
The base. The elevation of the cross-section.
Yeah, okay, you said the elevation, so you're just talking about the height of it, right? This y value is changing the area of this cross-section. How do we find the area of a cross-section, of this cross-section? That should be quite simple, because you know the shape. The shape is a square. How do you find the area of this square right here? S squared. Okay, so you guys know, if you had a square, you might just go length times width, or base times height. And you forget that actually we can say S squared because it's a square, and both of them are the same. So if we wanted to find the area of a cross-section, we would just have to take S and square it. But the S is changing. And how is the S changing? The S is changing because of the Y. So how can we relate the Y and the S together? And in math, when we say how would we relate two variables, we want to write an equation somehow that would relate those two variables together. Now this is the hardest part about cross sections and finding volumes. Right here, this is the hardest part. How do we relate the Y, which is what you guys told me earlier? The Y is what's changing, and so is the area of the cross section. And with the Y changing, the S is changing, which is what's changing the area of the cross-section. How do we relate the S and the Y together? And that's when we pull out similar triangles. And so we have this one really big triangle right here. I'm going to draw that first. Then we have a smaller triangle. The smaller triangle is actually really small because I put it up top. Actually, let's do it in red so we can see it easier. So that's a little tiny triangle right there. So how do these triangles relate to each other? Well, we know they're similar. We know they're similar because they both have a right angle and they both share this angle. So we know they're similar. As soon as you have AA, angle, we know that those triangles are similar. So what are the labels on some of those sides? We know the length of that side. What is that length? It's 2. And then we know the height right here, which is 12. What's the height for our little one? It says it right here. 12 minus y. And what's the bottom leg of this triangle? What's that bottom one right there?
1/2.
Yeah, it says it right there. It gives it to us again. So 1/2 s. Okay, so now let's set up a proportion. Because once we know that the shapes are similar, we can set up a proportion. So we got, let's see, we can say 12 over 2 equals 12 minus y over 1/2 s. Okay, we do some simplifying. So we would get rid of this 12 and this 2. That 12 becomes a 6, the 2 becomes a 1. And then we could cross cancel. So 6 times 1/2 of s, that's going to give us 3s. And what is 1 times 12 minus y? Yeah. Does he really want us to answer? Okay. And then if we get the s alone to see how we can get s, we would get 4, because 12 divided by 3 is going to be 4. And then we get 1/3 y. So this is actually a function that will give us the value of s. Now, how is that helpful? It's helpful because now we can find the area of any square. How do we find the area of the square? We just take the side and we square it. So we got to take this, whatever s equals, and square it. If I go like this, if I say 4 minus 1/2 y, oh wait, thank you, 1/3. 4 minus 1/3 y, and I square it, that'll give me the area of any square, right? So how does that relate to what we're trying to do? How does that relate to finding the volume? Well, here, let me show you guys this. What was the area function for the bottom of this shape? We wouldn't call it a function. It's kind of weird to call this a function. 20. That's a really simple function. Why is that function so simple? There's no variables. That's a constant function. So this function is 20. And what did we do with that 20? We added it to itself 4 times because we knew there was 4 layers. Now this is the function of the area of the base. And that's the, sorry, I spelled base wrong. That's the hardest part about doing this cross-section thing, is finding the area of the base function. Let me write function. Area of the base function. Now, do we have the, yeah?
So the area of the base function is like how fast the cross-section changes?
Close. Now, when the cross-section changes, the area of the base function changes with it. So this one doesn't change. It's constant. And we can tell just by looking at the picture. It's kind of obvious. But when I go back to what we were working on before, now we have something that looks a little more complicated. This is our area of the base function. So I'm going to label that guy too, because this is the hardest part about this. We're going to call this the area of the base function. Oh, but wait a second. There's a better word for base. What is it? Instead of saying base, what do we say? Cross-section. Area of the cross-section formula. And once we find the area of the cross-section formula, now we can take that function and we can find the area of every single piece of paper that we stack on top right here to find the total volume of it. So how are we going to plug in a number? Like, what numbers are we going to plug in order to find the volume of, or the area of every single piece of paper?
All the numbers between 0 and 12.
All the numbers between 0 and 12. Now, is there an easier way to do that instead of plugging in every single number? Yeah, we take the integral. I'll answer your question in a second. Hold your thought. Don't lose it. So I could take the integral from 0 to 12 of 4 minus 1/3 y and square it. Now, I did all this talking just to get to this point so you guys would understand what we're doing. We have the area of the cross-section function in there, and then we have from where to where that it's going in order to find the total volume of this shape. Now the job becomes simple because we just use the fundamental theorem of calculus from now on. We can simplify this stuff right here. This says squared, so you're going to go 4 minus 1/3 y times 4 minus 1/3 y, and you'll get a simple polynomial function, and then you're going to take the antiderivative of that. Okay, so go ahead and solve this using FTC1 right now, and I'll throw up the answer so you guys can check to see if your work is correct. Alright, so you'd go 4 minus 1/3 y times 4 minus 1/3 y. Always try to do manipulation, simplifying, before you think about use substitution or anything like that. So here we can multiply. We get 16 minus 4 over 3y, and then we get minus 4 over 3y again, and then we multiply that one times that one. The last one, you're going to get positive 1 over 9y squared. And we're taking the antiderivative of this. Actually, there's some simplifying I could do there. Let me rewrite it. Minus 8 over 3y plus 1 over 9y squared. dy 0 to 12. Alright, so we do the antiderivative. We get 16y minus, that's going to be y squared. I always like to write the variable and a new exponent first, so then I can see what I have to divide that number by. But because it's already a fraction, I'm going to multiply it by 1/2 instead. And so we have 8 over 6 plus y to the third. We get 1 over 27, because 1 over 9 times 1/3, or divided by 3, equals 1 over 27. And I'm going to plug in 0 and 12 to get my answer. Now I don't have to plug in the 0 for this one, because the 0 will get rid of every single term right here. So all we really have to do is plug in this 12, and that's going to give us the total volume of this pyramid. So we plug in the 12, you get 16, you plug in 12 right there, minus, that simplifies to 4 over 3, you plug in 12 right there, plus 1 over 27, and we plug in 12 right there. Well, that's going to be a big number right there. And so you get 64? That's it. 64 is your answer.